multiplication rule. Oh, I can see already I'm going to need a bunch of blank slides. So that's probably enough. Oh, that's working. Here we go. Multiplication rule. Let me give it to you right off the bat this time instead of, last time I kind of led up to it, but just for the sake of time, let me give you what the multiplication rule says. It says probability of A and B equals probability of A, what do you think? Times, yes? That's why it's called the multiplication rule, ladies and gentlemen. Times what? The probability of, well, you won't get this. What do you want it to say, but it doesn't quite say? You wish it said the probability of B. Wouldn't that be a nice rule? Here's what it says. It says this funny symbol. So I need to explain what that means. The way you read that is the probability. Interesting you say divide, because there's ways I can go with that mathematically. I won't. This is a straight line. And it says the probability of B given A. Given. Meaning, we know event A happened. We know event A happened. Okay? So, example. Well, yeah, I could, but Prop 22 is getting ridiculous. Let me do this instead. Let me make up my problem. I like this example better. So I have in my pocket, or I have in a bag, one quarter, one dime, one nickel, one penny. A coin is randomly selected. And of course, what does that mean? Equal chance for any of those, right? So then I could do this. I could compute the probability of Q, where Q is the event that I choose a quarter. Right? So what's the event that I choose a quarter? That means I reach in the bag, I pull out one coin. What would be the probability of Q according to our theory? 1 out of 4. Who follows that so far? Right? Because we said randomly. Okay. New problem. 2 coins are randomly selected. Instead, let's say 2 coins are randomly selected. So this is easy, we're saying. We get that. Okay, if 2 coins are randomly selected, what I want to compute is the probability of Q and I'll call it capital N. Do you know what I mean by capital N? The event that I choose what? A nickel. Now wait a minute. Explain what this means to the person next to you. I'm trying to compute what are the chances that when I reach in and pull out 2 coins, I get what? The quarter and the nickel. Talk to someone near you about what that is. What do you think that probability is? Okay. I'm going to walk you through this. Ready? Ready? It's the probability of Q times the probability of N given that Q occurs. Now, it's going to equal, what's the probability of Q occurring? We already computed that. That's 1 out of 4. We could, but I really want the fraction for, you'll see why. You'll see why. Yes, it's 0.25. What's the probability of N given that Q occurs? See, here's the thing. Think of doing it separately. First, you take out the quarter. You have to have the quarter to compute this probability. How many coins are left? You know what this probability is? 1 out of 3. So it's 1 out of 12. There's the multiplication rule. Now, hang on 1 second. We could try this experimentally. It's actually pretty cool. If you take the coins in a bag and pull out 2 at a time, you won't usually get the quarter and the nickel. You will sometimes. If we did it thousands and thousands of times, the law of large numbers said that if you graph the relative frequencies, you know how high that little bar would be for Q and N both happening? It would be 1/12. And that's what would happen, or pretty close to 1/12. It wouldn't be 1/16, like you might think. Now, final 2 minutes gives me just enough time for my last experiment. Thank goodness I made up my own, because this wouldn't have happened otherwise. Here we go. How about this? A coin is chosen, replaced, then another coin is chosen. Well then, the probability of Q and N is the probability of Q times the probability of N given that Q occurred on the first pick, right? But here's the thing, guys. Oh, times, sorry. Times. Probability of Q, we said, is 1/4. But now, what's the probability of N given that Q occurred? It's still 1 out of 4. You guys with me? So then you'd get 1 out of 16. And if you tested it, that's what you would get. And the interesting thing about this is that notice in this example, the probability of N given Q equals the probability of N. Right? It's just the probability of N occurring in anyways. Right, because the quarter was replaced. So in this example, we say N and Q are, and here's the big word, the big vocab word for this section, they'll call them independent events. Why do they say independent? Because one doesn't affect the other, because you put the one back. But in the first example, the probability depends on what happens. Okay? Hopefully that'll get you through the homework. You take a look at the tree diagram up here. Here's an example. This figure summarizes the possible outcomes for a true-false question followed by a multiple choice question. Imagine on your last exam, I ask a true or false, and then I ask a multiple choice where you could answer A through E. How many different answers could there be? Well, over here on the right, it says, note there are 10 possible combinations. True A, true B, true C, true D, true E, right? False A, false B, false C. So it's not always multiplying by 2, but it is multiplying by the number of possibilities, that 5. Does that make sense? So that's what you're looking at. Sure. If you had 3 possibilities there, and then 5 for the next one, there'd be 15. You can see from the tree why we multiply, right? Because everything's equally likely to happen, so you could just see the 5 is being multiplied by the 2, because here's a 5 and there's a 5, right? You can see why the multiplication rule works. Okay. Again, this is the multiplication rule I've been giving you. Note that if A and B are independent, what does independent mean? It means P of B given A equals P of B. And so in that case, you could replace this with just P of B. Fine. I worked on a problem last time. Things in a bag. I'm not going to do that again. When Sonia asked that question about the one, and we said, or no, on the one I had here, it was number 4. One of you guys asked it. And you said, why can we treat them as independent? This is the guideline. If the sample size is no more than 5% of the size of the population, treat them as independent even if technically they are dependent. Okay? And I'll show you what I mean about that in a second. Let's do it here. Let's find the probability of choosing 2 aces when I pick 2 cards from a standard deck. Now, the problem with using this example is we're not all so familiar with cards anymore, so I'm going to give you some details you need to do this problem. A little help from the audience. You guys know how many cards are in a standard deck? 52. 52 pickup, right? So I want to choose 2 aces when I pick 2 cards, right? Easier problem. Let's let A be the event that the first card is an ace. And let's let B be the event that the second card is an ace. Okay, and what am I trying to find? Probability of what? A and B. So this is the probability of what? A. It's times, because this is an and problem, right? So if you have an and, that tells you multiplication rule. Times what? Probability of B given A, and I have to say what that is. Right? Now, this probability, what's the probability of picking an ace? Well, isn't it something out of 52? 4, because there's 4 aces, right? So 4 out of 52. Now, here's the tricky part. What's the probability of B given A? Very good. It's 3, because there's 3 aces left out of 51. And so I'll take out my calculator and work out what that is. So let's see, I'm going to do 4 out of 52. That's about 7%. I'll do 3 out of 51. That's about 5%. Right? Oh, but I'm going to multiply those together. So let's see. 4 divided by 52 times 3 divided by 51. And by the way, if all you're doing is multiplying and dividing, this is fine to just write it straight across like that. It's when I start putting in the plus signs that I have to worry about order of operation. Let's see what we get. Ooh, not very likely, is it? 0.0043? Is that what it said? Let me see that again. 452? 452, yeah. Wow. Not very likely. The other thing that we could do, remember, with these calculators, we could change to a fraction. I'm just curious. 1 out of 221. So very unlikely. Now, our guideline said if the probability, if the sample is less than 5% out of the population, then don't worry about, you could treat them as independent. Let's see how that would work here. Because here, how many cards did I pick? 2 out of how many? And 2 out of 52 is only about 4% of the cards. Okay, see that? So they're saying, hey, treat A and B as independent. Now, if you treat A and B as independent, then the formula would be P of A and B equals P of A times P of B, because P of B would be the same as this, right? Now, we know that's not quite true. But sometimes you know P of B, but you don't know P of B given A, and so this is easy to do. I could do 4 out of 52 times 4 out of 52, right? And get an answer. Let me do that on the calculator. 4 out of 52 times 4 out of 52. Oh, 0.0059. On the calculator, how do I? Let me show you that. I'll do it right now. To make it a fraction on the calculator, if I hit the math key here, choice number 1 says change your answer to a fraction. 1 out of 169. But look at it this way, guys. For practical purposes, is this answer pretty close to this answer? I mean, think of it this way. What percent chance is there of picking 2 aces if I pick 2 cards? About 0.5%. Less than 1%. You guys with me on that? Now, if I do this way, this is not correct exactly because I pretended they were independent. But isn't the calculation pretty darn close? It's still about 0.5%. So what we're saying is if you have a situation where the sample is less than 5% of the population, we'll pretend that the events are independent and get pretty good results. That's the idea. Rick?
Do we always do that, or in situations like this where it's easy to do calculations, should you do it?
Yeah, I guess if you can go ahead and do the actual calculation like we did, it's better. Right. But in the book, for example, when we're picking things off of an assembly line or testing certain drug samples or things like that, you may have to do this. Right. Absolutely. No, I don't care about it. Matter of fact, I would prefer in this case you did not change it to a fraction. And the reason is, do these fractions mean very much to you guys? They don't mean a whole lot to me. 1 out of 169. You know what I do it automatically? Is I change it to a decimal. Because to me, when I see this, 0.000, it's about 0.5%. That means something to me. So it's interesting. You can go back and forth, sure. So it's all, statistics is all about meaning. We're trying to speak language to each other and create meaning. And so that, in this case, yeah, I think I'd stick with the decimals.